What? All right. What? Yeah. Logged in like 10 minutes ago.
Okay. All right, so here we are again. Let me just get Moodle open. All right, so let's get, I'm going to open up Moodle. Oh, wait, I don't think that's. There we go. That's Moodle. All right, here we go. All right, so yes, we're still in the middle of chapter 11. It's going to last for a while. It's a very long chapter. So what I do want to mention, though, is that at some point we have to start thinking about a second midterm. So the second midterm would be based on chapters 4 and 5. And now we're done with 5. The emphasis will be on chapter 4, though. As far as the chapter 5 is concerned, the trigonometric functions, I was working on the sample midterm last night, and I realized that, I think that most of the questions will ultimately end up being in chapter 4, which is our discussion about logarithmic and exponential functions. And there'll be some questions about trigonometry, but it will be very heavily de-emphasized. It's just enough that you understand how those functions work. And when if you see them again, let's say in Calc 1, it's important that you remember how they work, but it's not going to be terribly strongly stressed in this class. Okay, so I was almost done with the sample midterm. It's not 100% done. So expect to have it ready in the next day or two. So maybe even tonight. I'll probably just put it up tonight, because if you look at the calendar, there's one thing we have to be careful about, because this class only meets once a week. As far as I know, school is not open on the Wednesday before Thanksgiving. In fact, why don't we do this real fast? Let's confirm that. Let's see, where's the old academic calendar?
Excuse me, can I ask a question?
Yes, go ahead.
Are you almost done grading the first midterm?
No, they were done a while ago.
Oh.
If you don't have a grade, that means I didn't receive it. That means you'll have to send it again.
Oh, okay.
Yeah, that happens a lot with email. So if you don't see a grade in there, that means that for some reason it never got into my inbox. And what you need to do is send it out again, because this happens not frequently, but it happens usually in each class. There's at least one or two that for whatever reason they just never make it through. And so if I couldn't find it, I couldn't grade it. Now, what I think you should do is send it like right now.
I'm going to do that right now.
Sorry, I have a question, because I also didn't get a grade, but I don't know which email to send it to because I've been sending it to the Gmail, but
Yeah, I don't know what's going on with that. Why don't you send it to my personal account, because
okay.
it'll be easier for me to see when it's there. And my Gmail account has so many emails that it's easy to miss one. And also, I've noticed that the Gmail account tends to put a lot of things in the junk box that shouldn't be in there. And if I don't notice it within a week or so, it just gets deleted. And I'm sure that's exactly what happened, especially if you have a large number of attachments. So try it again with my purchase account, which is Alan Anderson at purchase.edu. And then that way there's a chance that it won't get disappeared into the junk box and will actually get delivered. So, all right, let me just go back and open up my email. Yeah, I know. I mean, this is a constant problem with online classes. If Gmail was reliable, it would make things a lot smoother, but almost without fail, there's at least a few that, especially when there are large attachments, somehow it just disappears into hyperspace. And all right, so there's Arthur. All right, did you just send that?
I just sent that. Yeah,
I'm
'cause
doing.
I received
I'm
a graded
sending
review.
like the process right now. Like I'm.
All right. Yeah, it just, well, now it's there. Now, why wasn't it there before? God only knows why. You know, like I
Yeah,
said.
I forwarded, so that's why it says 2. So
Oh, here's
I guess-
Mateo. Did you, no, that's, wait a minute. Priscilla, did you just send yours?
Yeah.
Okay, and Mateo, this came in last night. Is this the one? I think that's a different class. Okay, never mind. But all right, anyone else? Yeah, it's really aggravating, but you know, but I have it now, and that's all that really matters. Okay, you're not going to be penalized or anything. I'll just grade it and then put in your scores. Yeah, it's a common thing. It's just unbelievable. You'd think that by now the technology would be in place, but that just is not the case. That's 3 that just somehow slip through the cracks. And then, you know, I search for them and I search and I look around and they're not. I think what happens is they go into the junk box for no reason. And then it automatically deletes them when they've been in there a few days, especially Gmail. I found that my Gmail account just throws half my stuff in the junk box. And even when I tell it that it's not junk, it continues to put it in the junk box. So like I said, the technology just, you know, it's so overrated. It just is not reliable at all. So, you know, that's why this app ends up happening. But at least now I've got them. And that's the important thing. But anyway, yes, as I started to say, the sample midterm is 99% ready. I was just putting some finishing touches on it. I'll post it today. And so when that's done, I started to look at the calendar. Yes, no, even before that, I was going to look at the academic calendar. So I'm all right, let's get it together here. The academic calendar, which is now gone, of course, here it is. So as far as I know, there's no class on the Wednesday before Thanksgiving. That's right. Now, today's the 10th. So that means we have today and we have next week before Thanksgiving. So let me just open this up and just confirm it. There's no point just saying something off the top of your head. All right. So we need February now. Oh, sorry. November. All right. So today's the 10th. Oh, look at this calendar. It starts on Monday. That's weird. Okay. So yes, we'll have today and we'll have next Wednesday and then we're off. And then when we come back, we've got Wednesday the 1st. And I think Wednesday the 8th might be the end. So let me just confirm that. Yeah, the 8th. Okay. So, all right. So, you know what? Let me just do this. Let me just put this in an announcement. Just so there's no doubt in anyone's mind. All right. So how about this? Remaining classes so that we can plan properly. All right, so at 11:50, we'll have classes on today. And then not on the 24th because of Thanksgiving, 12:1 and 12:8, and that's it. Okay. There will be no class on 12/24. Oh, sorry, 11/24 because of Thanksgiving. Okay, now that being the case, what we're going to have to do is, even though it's not completely ready yet, why don't we do this? Why don't we go over the sample midterm on the 17th? Now, obviously, nobody wants to work on a midterm during Thanksgiving, and you shouldn't have to. So here's what we can do. What if we have, oh, for God's sake, what if we have it due? Let's see, how would that work? Today's the 10th. If we go over the sample midterm on the 17th, you'll be out all this time. Why don't we have it due, let's say, I don't know, how about Friday the 3rd? That's more than 2 weeks. And no, all right, that sounds good. Friday the 3rd, okay? I think that's a good idea. So we will cover the second sample midterm on 11/17, and then the second midterm will be due on Friday, December the 3rd. As far as the finals are concerned, we're meeting one last time on the 8th, and the following week would normally be our finals week. We would normally come in on the 15th and have an exam in the classroom. But because we're not doing that, what we can do then is on the 1st, or the 8th rather, we can go over the final, sample final, Wednesday the 8th, and then we can have the actual final due, let's say on Wednesday the 15th. Although I might be able to stretch that out a little bit. It depends on when the grades are due. Maybe as you know, let's say Friday the 17th, but we'll figure that out later. So let me add this to my message, I guess, so we can have the whole schedule right here. We will cover the sample final on 12/8, and then let's say the final exam will be due on Friday the 17th of the 12/17. Okay. All right. How does that sound? Oh, Fernando. Yes, go ahead.
Quick question. The final, it would be the last midterm, like the third midterm, or no?
I'm sorry. I was reading somebody's message. What did you say?
Yeah, I was asking like the final midterm, like our final would be our third and last midterm, or would that be like?
It'll
or
be
like-
the last, whatever last two chapters we cover, and it'll be the same format as what we've been doing.
All right. Thank you.
Okay.
I just want to let you know, I just sent it out, my midterm out too.
Oh.
So yeah, I'm just letting you know.
Christopher.
No, John.
Okay, well, see, it's not here.
John,
Just
I sent it to your purchase email.
right. Yeah, that's all right. Let me just refresh it. Like I said, you just cannot count on it.
I don't know, like I'm looking at the old one I sent. It says sent to you, so it's like
Oh, it doesn't matter. It doesn't matter if you didn't make a typo. It might not come anyway. How long ago did you do that?
I just did it right now at 8:12.
You see what I mean? Let me look in my junk box. No, I guess
It has.
it just decided, oh no, that one isn't going through. And you don't get any warning about it. It doesn't come back and say, listen, I couldn't deliver it. It just goes and never comes to where, I mean, it's just so ridiculous. Well, I'm going to refresh it a couple more times, and then I'm going to have to ask you to send it again. You see what I have to put up with? How am I supposed to know that whether you sent it or not? And how are you supposed to know that it never got here? Unbelievable. Now it's possible that because it has a lot of attachments, it might take a little longer, but now we're looking at 3 minutes already. You know what, I've noticed what happens. If you send another copy right now, they'll both suddenly show up in about 2 more minutes. All right, I think we've given it plenty of time. Try it again.
Okay.
And then you wait and see, they'll both pop up in the exact same moment. Nope. Nope. Unreal. All right, in the meantime, one thing I also wanted to mention is that if I didn't already say so, the second midterm will be chapters 4 and 5. Okay, but the focus will be heavily on the exponential and logarithmic function with very little stress on the trigonometric functions. Okay, a little, but not much. Okay, so primarily it'll be based on 4. And then the chapter we're doing today is 11. And so let's get that open and we'll carry on with that. I think there's some videos that we didn't get a chance to watch. This is one of those areas where there's a lot of really excellent videos out there for this subject matter, and I'd like you to see some of them. I've got some of them posted here, but I think there might be more that we'll get to look at. Oh, this thing isn't done. Okay, so let me just mention that the second midterm is on chapters 4 and 5. With a heavy emphasis on chapter 4. All right, most of the questions are based on 4. All right, I think that's good enough. That'll do for now. So we're all set, I think. We're all caught up. So the only thing that remains to be done is for me to post the sample midterm tonight, because like I said, I was still not completely done with it, but it's 99% done. All right, in the meantime, just out of curiosity, let's see if this thing ever happened. Of course not. You might have to send it 4 or 5 more times. I'm serious. It's just unbelievable. You know what you do while you're at it though? Send it to my Gmail account too, just to be on the safe side. Between the two of them, it might actually show up at one of them. And I'll check the junk box as well. All right. And you know what you could do too? Just send me a plain email with no attachments that says, I am forwarding my midterm. That way I remember that this was going on. Okay. All right, let's get 11 open. It's so ridiculous that this is necessary, but it is. All right, so let's go. Yeah. Oh no, I was trying to get it. Okay, where's Moodle?
What's your Gmail again? Dr. what?
It's Dr. AA 2000. Yeah, 2012.
2012.
Right now, the doctor is spelled out. It's not DR. It's DOCTOR AA 2012 at
Okay.
gmail.com. So send it there too. And just, include a message that says, I'm sending you my second midterm. So I know to look for it. I'll say, hey, wait a minute. Wasn't he supposed to send it to me? And that way I remember that you did try. Oh no, these are people whose midterms were never delivered by email. I have yours. I remember seeing it. So if you don't have a grade for your midterm, it's because it never was delivered into my inbox. And so you need to resend it. Okay. That's what this is all about. All right. So let's get this going. Now, this is a very exciting chapter. We had a lot of fun with it so far. And there's plenty more fun where that came from. It's a very interesting topic. So let's get 11 open. And we'll pick it up where we left off. I seem to remember that we got all the way as far as combinations. Let me just jump up ahead to combinations. We did permutations for sure. I think, did we finish combinations? Oh, here we go. Yes. Yes, I think we left off right here. We're starting probability theory. Okay, so everything we did up to that point really belongs to a branch of math called combinatorics. Let me make a note of that here. So combinatorics is a specialized area of mathematics. It shows up quite a bit in computer science. So combinatorics is a branch of mathematics that deals with counting. That's really what it is, counting techniques. So arrangements, permutations, and combinations are all part of the field of combinatorics. So I just wanted to let you know that this is what we've been doing, but the reason why we study this now is because it provides us with the background we need for what is probability theory itself, which is itself another separate branch of mathematics. And so what's happening with probability theory? Well, first of all, what we're trying to do is quantify uncertainty. All right, in other words, we want to be able to say, listen, we have all these uncertain events, and we want to know what is the likelihood of them happening. And it's a very challenging area of study because obviously, you know, we never will know what's going to happen in the future. The best thing we can do is try to figure out what might happen in the future and assign those possibilities, possible outcomes, different probabilities. So we start out by introducing the concept of the random experiment. So random experiment is just a process, we'll call it, where outcomes are being generated, but in such a way that before this process starts, we know what might happen, but we of course do not know what will happen. If we knew what was going to happen, this wouldn't be random, and none of this would be necessary, okay? If we could see the future, the whole area of probability theory would be completely unnecessary, okay? But obviously we can't, but at least we can try to figure out what might happen in the future based on our understanding of the process. Now, there's several good examples of this. Now, it turns out that gambling games lend themselves very well to this type of analysis because of the way they're structured. For example, spinning a roulette wheel. If you've ever seen a roulette wheel, in fact, let me show you a picture of one if you're not familiar with a roulette wheel. It's a game that you can play, usually in a casino. And what you'll notice is that you're spinning this gigantic wheel. Oh, I thought I could make it bigger than that. Oh, there it goes. Okay, so if you look at the wheel, you'll notice that what's on there are numbers. Now, there's a little ball that will be tossed out there, and it will spin around and around and around, and it will land in one of these slots in front of one of these numbers. Now, the numbers range from 1 to 36, of which half are red and half are black. And then on this wheel, at least, there's a single green number, 0. That tells me that this is a European wheel. In the United States, there's also a double 0, which is also green. And what happens is before the wheel is spun, you place your bet on what you think will happen. You can bet on a single number, for example, or whether the number will be odd or even, or red or black, or you can bet on the 0 and double 0. And if you're right, you win money. And that's how it works. But the important detail here is that with an American roulette wheel, there's 38. Yeah, here's one. You can see this one has the double 0. Oh, wow. Ooh, that one's huge. Okay, it has the double 0 as well as the 0. That's an American roulette wheel. And even though you obviously don't know what's going to happen, you at least know that these are what the numbers that could turn up, and each one is equally likely to show up because that's the way the wheel's been designed. And so with 38 numbers, that implies that each number has a 1 out of 38 chance of turning up. Okay, so that's the key detail. We know that a number from 1 to 36 or 0 and 00 will turn up. Each one is equally likely, so therefore each one has a 1 out of 38 chance of turning up. All right, that's an important detail when you place your bet because you have to understand how this works. Otherwise, you're just going to gamble away all of your money. And even as it is, you might do that anyway. Okay, just because you understand this doesn't mean you're going to win money. All right, now hold on a second. I have to find my stylus here. There it is. Okay. All right, so let me just make a note here. Each number has a 1 out of 38 chance of turning up. And that is what we mean by random experiment, okay? So in other words, we know what might happen. And we also know the probabilities of all these outcomes, but we just don't know what will happen. What about choosing a card from a deck? Same thing. It's a randomly shuffled deck of cards. There's 52 cards in the deck. Each one has a 1 out of 52%, it's not percent, sorry, 1 out of 52 chance of being selected. So each card has a 1 out of 52 chance of being selected. Now, rolling a pair of dice is a little bit trickier because, you know, we have to sit down and think about how many different things can happen with a pair of dice. Now, everybody knows, I guess, that a single die has 6 spots on it, ranging from 1 to 6. So if you wanted to know what might happen with a pair of dice, you could actually express that as ordered pairs. In other words, the outcome 1, 1 means each die turns up 1. But if you have something like this, 2, 3, that means the first die is 2, the second die is 3. So by doing that, if you were to write down all the possibilities, you would discover that there's actually 36 things that can happen with a pair of dice. Okay, so in other words, what would they be? You could have 1, 1, 1, 2, and that would go all the way up. We don't need to write in every single one of them. 1, 6, then, so in other words, the first die could be 1, the second die could be 1, 2, 3, 4, 5, or 6. And you could have 2, 1, 2, all the way up to 2, 6. And then this would go on for all of the numbers from 1 to 6. In other words, 3, 1, 3, 2, all the way down to 6, 6. So the last outcome is going to be, you can see we have to go all the way up to 6. And that, even though I've left out a bunch of them, just to save time, that adds up to 36. So there's 36 different ways we can roll the dice. Now, normally in a game of chance, you're interested not so much in the actual rolls themselves, but their sums. That's normally how games with dice work. What we're interested in is in the sums. So imagine yourself playing a game where you'll win a prize as long as you get an 11 or a 12. So the question becomes, how would that happen? How many different ways can that happen? So what you would need to do then in order to determine the probability of getting a particular sum, we can add up the number of ways of getting that sum and then dividing by 36. For example, the probability of getting at least 11 would be, all right, so how many different ways can this happen? You can get a 5 and a 6 and a 5, and a 6 and a 6. So that would be 3 out of 36. So imagine, like I said, you're playing a game where winning a prize depends on your getting at least an 11. Well, at least you know that the probability of that happening is 3 out of 36. It's not much. It's not a very large probability, but at least we know what it is when we decide whether or not to play this game. So all of the different sums that you could create with 2 dice, we can easily calculate their probabilities by counting up how many ways we can get that sum and then dividing by the grand total, which is 36. 36 different ways of rolling the dice. Now, there's a lot of other possibilities too. And they don't all necessarily involve games of chance. For example, how about this one? Is another example of a random process. Suppose that a manufacturer produces spare parts. Each part has a 1% chance of being defective. Okay, so in this case, the parts represent a random process because we know in advance that each part has a 99% chance of being good and a 1% chance of being defective. But we don't know in advance which parts are good and which are defective. All right, so it's a random process. We just watch the parts coming off the assembly line, knowing the probabilities that they are defective or not defective. So in a case like that, suppose you said to yourself, listen, in a batch of 100 parts, what's the probability that none of them are defective? Well, you could figure that out because you have all this information. And so it could be a very useful thing. Like, let's say you are actually producing these parts and you want to keep the number of defectives down to a minimum. And you want to ship the parts off to the customers without having to worry about defectives. So you should be able to get a sense of how likely it is that there will be a certain number of defective parts. Anyway, so that's the concept of the random experiment. So what we're going to do here is we're going to use a very simple case to illustrate these principles. So imagine a scenario where we roll the die twice. But this time, we're only interested in whether the numbers are even or odd. So in other words, we're not paying attention to the individual numbers, just whether they're even or odd. So what that does is it dramatically reduces the number of possible outcomes from 36 to just 4. Okay, now, for example, let me show you in the next slide how that would work. We could get an even followed by an even followed by odd, even odd, odd even, and then finally odd odd. Okay, so in other words, the even represents the rolls 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, 6, 2, 6, 4, and 6, 6. So you can see that takes the place of 9 actual rolls of the dice. So that's why there's only 4 of them. Each one of these actually takes the place of 9. So we reduce the entire set of possible outcomes to 4 because it's just a little simpler. And so it'll be much easier to calculate the results in what will follow. All right. Oh, I just threw that in there in case you were wondering. The word, a single die, one die, the singular is die, the plural is dice. Now, because each of these outcomes represents 9 actual different rolls, that means each one of these has a probability of 9 out of 36 or 1/4. All right, and because each of these outcomes is equally likely, so we have 36 possible outcomes when we roll the dice, each one of which is equally likely. So therefore, if even actually represents 9 different outcomes, each of which are equally likely, that implies that this probability is 9 out of 36, which is 1/4. And that's true for all 4 of these. We're not going to go through the entire list each time, but it's just, you should be aware that each one of these has a 1 out of 4 probability of occurring. And that makes our results a lot simpler. We can also do examples where they're not all equally likely, but for now, we'll stick with this case because it'll just be a little bit simpler. We can complicate this as much as we want later on. All right, so just keep that in mind. Each one of these has a probability of 1/4 of occurring. All right. Oh, by the way, here's a little binary chart as a table, binary tree as it's called. And what this is going to help us do is figure out how many different outcomes will occur depending on how many times we roll the dice. So if we roll the die once, we can either get even or odds, each with probability 0.5. If we roll it a second time, as we've just seen, then the number of outcomes goes to 4, EE, EO, OE, and OO. And you can see why, because starting from an E in the first roll, that can be followed up by either another E or an O. With O, if we had an O to start with, we can follow that up with with an E or another O. And if we decide to roll a third time, the number of possibilities goes up to 8. So starting with 2 evens, we can have another even or an odd. EO is followed by an E or an O, et cetera, et cetera. So with 8 of them, each one has a probability of 1/8 or 0.125. So the tree is designed to help us not lose track of them all because, it's easy. When there's a lot of outcomes, it's easy to lose track or forget some of them. So with a binary tree like this, which by the way, it only works when there's 2 outcomes in each roll. I guess you could do this with 6 with the original die roll, but this is so much simpler. You can see how many there have to be. And by the way this is written, it should be clear that if there was a 4th roll, there would be 16 possible outcomes. And the logic there is that you're just doubling the number of outcomes every time you roll the dice, but only paying attention to even and odds. Okay, so let me just make a note of that here. So when rolling a die and only paying attention to evens and odds, every roll doubles the number of possible outcomes. Okay, so every time you roll the die, you're doubling the number of outcomes. So with 2 rolls, there are 4 possible outcomes. With 3 rolls, there are 8 possible outcomes. With 4 rolls, there are 16 possible outcomes. Okay, so just double every time. Now, when you roll the die and actually look at every number, that's a different matter altogether. When rolling a die and paying attention to the individual numbers, each roll multiplies the number of possible outcomes by 6. Okay, so with a single roll, there are 6 possible outcomes, obviously. With 2 rolls, there are 36 possible outcomes, as we've already seen. Now, here's the interesting one. Most games, you only use 2 dice. It's very unusual to have 3 dice, but they do exist. With 3 rolls, there are 216 possible outcomes because you're just multiplying 36 by 6. So you see how this works. You're multiplying by the number of possible outcomes on each repetition of this experiment, or each trial as it's called. Okay, so this is how it works. This is how the number of possibilities is counted. In the case where you're rolling a die with 6 sides, every time you roll the die, you're multiplying the number of outcomes by 6. What about flipping a coin? Well, flipping a coin is just like rolling the die and only looking at evens and odds. Okay, so when flipping a coin, each flip doubles the number of possible outcomes. Okay, so if you want to build a little chart here, I'll do that right now. You could have 1 means 2 outcomes, 2 goes to 4, 4 goes to 8. Oh, sorry, what did I do? 3 goes to 8, 4 goes to 16, et cetera, et cetera. And if you notice, and here's the key to the whole thing, this will help you remember this. This is nothing but 2 to the first power. All right. So now making superscripts in PowerPoint is kind of a headache here. So let me just show you. All right. So hold on one second while I fill this in as painlessly a way as possible. Okay, so that's the pattern. All right, it's just 2 to the exponent is the number of flips, and that's because there's only 2 possible outcomes. All right, now, whenever we conduct an experiment, there's always going to be a group of different possible outcomes, as we've seen. We're going to gather them together into a very special type of set. This set is known as a sample space, and that simply defines for us all the different possible outcomes of our experiment. So that you can see how this is a set because it has these braces here. And that means that this is simply a collection of objects where the order in which I've put them has no bearing on what this is equal to. So it's just a group of objects. And here, those objects are the 4 possible outcomes of my experiment. So we call this the sample space. And each element is sometimes called the sample point, although sometimes we simply call them elements, and they're all referred to as outcomes. because they represent one thing that can happen when we conduct our experiment. Okay, now the sample space will help us to calculate probabilities. In this case, like I said, it's a very simple example because each element in there is equally likely to occur. All right, let's see. Now, just because, you know, it's possible that it's been a while since you thought about sets. What we really are interested in here is reviewing algebra or algebraic operations on sets. So what I've done here is I put together a small collection of sets. You can see A is 1, 2, 3, B is 2, 3, 4, C is just 5, D is 1 and 2. So you might remember the first algebraic operation that you normally perform on sets is called union, and it's represented by this U, all right? And what it represents is a new set that consists of the two original sets combined into a big new set. So if I try to apply the union to A and B, I've got a new set that contains the elements 1, 2, 3, and 4, because that represents all the elements in A and B. Now, if you notice, they both have a 2 in them. I did not write it twice. There's no need to do that because it's understood that the set only shows the unique elements. Okay, so the number of times each one appears is irrelevant. What matters is that I've got a 1, a 2, a 3, and a 4. And so this is defined as the union of A and B. Now, you may have seen this. Some books use, instead of the union symbol, they use the word or, because logically it means the same thing. A union B is a set of all elements that belong in either A or B, or possibly both. So we often see unions being used in set theory. And again, all it really means is you're bringing the sets together. Now, another important operation that could be performed on sets is this one. If you notice, this is basically an upside down U, and it's called intersection. And so when you apply it to A and B, you can see that what we're actually doing is looking for all the elements that the two sets have in common with each other. And in this case, that happens to be the 2. So this represents all the elements that are in both sets. And this one is often written with the English word and. Okay, so intersection and mean the same thing, because what we're looking for is all the elements that are in A and B. One is not good enough. All right. Is there another operation we can perform? Well, the answer is yes, but before we do that, I just want to show you one more interesting example. Right here. Suppose that instead of A and B, I want to know what is the intersection of A and C. Well, that's a very different ballgame, because if you notice, A and C have absolutely no elements in common. And that, when that happens, when we have a set that contains no elements, like we do here, we call that the empty set. And by the way, directly below it, you'll see the 0 with a slash through it. Many math books use that symbol instead of the brackets or braces, actually. They both mean the empty set. Okay, so let me just remind you again. I said the wrong thing a second ago. These are braces. These are brackets. All right, So they often play the same role in math, but we normally see the braces used for sets. So we'll stick with that convention, but with the one exception though, this 0/ is often used to replace the two braces with no elements. I don't know. I guess it's a matter of personal preference, but they both represent the empty set. Now, in this case, there's some special terminology that we need to know. Two sets like this that have no elements in common are said to be mutually exclusive. So you can think of probably a lot of examples of this, like the odd and the even numbers are mutually exclusive. Let's say the teams in the American League and the teams in the National League are mutually exclusive. You know, it's not that difficult to think of examples of two sets that are mutually exclusive. It just means they have nothing in common. All right, now on the next slide, we're introducing another key concept. This is not so much an operation, but it represents a particular relationship that can hold between two different sets. And that is the notion of the subset. What is that all about? Now, by the way, it's hard. This symbol is meant to represent subset. It's very hard to draw it without making it look like a C. You have to be careful with this one. You can see right here that sideways, all right, I'll put, I don't know what to do about it. I mean, you just have to be aware this is a subset symbol. Maybe I could draw it a little differently. Yeah, I guess that's a little better, but that is meant to represent subset. And what does it actually mean? It means that one set is completely contained within the other set. For example, DNA. With D contains 1 and 2. A contains 1, 2, and 3. Since all the elements in D are also in A, that means that D is a subset of A. All right, and you can think of a lot of examples of subsets. Like, for example, our class is a subset of the entire student body at SUNY Purchase. Okay, everyone in the class is also going to SUNY Purchase, and therefore this class represents a subset of the entire student body. Now, obviously, not all sets are subsets of each other. Or like, here's all right, I made this one up on the side here. What if A represents all SUNY Purchase students and B is all the art majors at SUNY Purchase? Well, then clearly B is a subset of A. All right, now I started to say that not all sets are not all sets are subsets of other sets. Let's look at this case. What about, instead of DNA, what if I try to compare C with D? Well, C and D do not have anything in common. Certainly, the elements of C do not belong to D. So in that case, we say that C is not a subset of D. And the way we indicate that is to take the subset symbol and just put a slash through it. Okay. So subset is the circle. I mean, the symbol with a slash through it means not a subset. Now, oh, by the way, I do want to introduce one more idea here. This is a graphical representation of sets that you probably run into before, but it's awfully useful for representing set theory. These are called Venn diagrams. And these are used to illustrate the relationships between sets. So for example, let's try a general Venn diagram. Let's say we have two sets A and B. Each set is represented by a circle. The entire box is the sample space. So what I'm going to do is shade in two different important concepts. So this shaded region that I've just shown you is A union B. Oh, sorry. Whoops. My mouse is broken. I'm trying to use this trackpad on here and it's really clumsy. Fortunately, my new mouse is going to arrive in the mail this afternoon, but I hope this never happens again. I can't stand this trackpad. It's so awkward. But anyway, the intersection between them, I'll illustrate with the cross hatching. And that is A intersect B, where they overlap. Now, you can see, I mean, it's a very simple idea, but these are so useful for illustrating the relationships between sets that's why they're so heavily used. Now, let's try another case. And of course, it's nice that anybody can draw one of these. I mean, they're not that complicated, but they illustrate the ideas very nicely. Here's an example of what I mean by that. Here are two sets that have no elements in common. So A intersect B is the empty set. No elements in common. And of course, we remember that this means that A and B are mutually exclusive. And we can shade these in, but you'll notice they have nothing in common. So when you see a picture like this, it's very obvious that they are mutually exclusive. All right, there's one more situation I'd like to illustrate for you with these Venn diagrams. And so you'll see what it is in a second when I finish drawing it. Oh, sorry. Yes. So the idea here, it looks like a hard-boiled egg, doesn't it? But the idea here is that B is a subset of A. Because B, every element in B is an element of A. And, or you can think of it as B is completely contained within A. So again, this could be these art majors at SUNY, and then A would be all the SUNY students. All right, so sometimes this can be very useful to illustrate, like we're going to see some more complex ideas in a few minutes, and sometimes these graphs can help us understand them a little more clearly. Okay, so, all right. Now, all of this buildup was very important because the next concept, which is a very important one in probability theory, is based on set theory. And so that would be the concept of the event. So an event, very simply, is a subset of the sample space. So this is why it was so important to review set theory so that we understand what the concept of subset is. Okay, it simply means one set is contained within another. In these examples, all of these events are simply subsets of the entire sample space. So therefore, if you notice, I've defined the event F as at most even one even number turns up when I roll the die twice. Basically, what that means is every outcome except two evens. And if you look at the bottom, I've listed them all. EO, OE, and OO are all qualified. And you notice every element in F also belongs to S, which implies that F is an event. All right. Now, let me just show you an example of something that would not be an event. Suppose I defined, oops. G, 3 evens turn up. And that would mean G equals EEE. Now, if you recall, the sample space is EE, EO, OE, and OO. Since G is not a subset of S, G is not considered to be an event. Okay, now that being the case, we can't calculate its probability, or we can think of this as having its probability is 0. Okay, in other words, if you roll a die twice, you cannot get 3 evens. So its probability is considered to be 0. Now, if the sample space was different, if we had rolled the die 3 times, that's a different matter altogether. But because we only roll it twice, it's not possible for G to happen. So therefore, it's not even an event. And we say that its probability is 0. Okay, or we can think of that as impossible. Okay, so when you say that something's probability is 0, that means it is impossible. All right, so let's just focus on the actual events. Now, what are we going to do with these events? Our ultimate aim is to calculate their probabilities. So, all right, and so here, just one more time, this is what F consists of. Now, you might recall us saying earlier that each of these outcomes has the same probability, which is 1/4. Why is that? Because each one of these represents 9 different rolls of the dice. So since there are 36 different rolls, for example, OO represents 1-1, 1-3, 1-5, et cetera, et cetera. Each one of these has a likelihood of occurring of 1/4. So therefore, and I summarize that right here, each of these outcomes, by definition, because of the way the experiment was performed, have a probability of 1/4. What does that do for us? Well, therefore, we can make the claim that because F contains the elements of EO, OE, and OO, the probability of F is simply equal to the probability of each of those outcomes added up together. Okay, so in other words, the probability of F is the probability of getting EO or OE or OO So we're going to combine all those probabilities and we come up with either 3/4 or 0.75. Now that seems pretty straightforward. And you can always use this approach to calculate any probability that you might need. But in this case, when we have 4 outcomes, all of which are equally likely, there's actually a shortcut that we can use, but only because each outcome is equally likely. Most of the time they won't be. And the approach we just did will be the way we have to go. But if we get lucky and all the outcomes are equally likely, here's all we have to do. Just count them, okay? So in other words, F contains EO, OE, and OO, whereas S has these elements. What I'm going to do, say the probability of F is the number of elements in F, which I'll define as NF, and that's just 3/4. All right, so when the outcomes are equally likely, then we can use this very simple formula. So, when they're equally likely, we may as well take advantage of it, but just be aware that most of the time we won't get so lucky. All right, so here's another quick example with a different sample space. Now, what if I increase the number of rolls to 3? But remember, I'm only paying attention here to whether they're even or odd. As we predicted from earlier, when we roll again, we're going to double the number of outcomes from 4 to 8. And so that's the list right there of all 8 possible outcomes, but they're organized in a special way. What I've done is I've organized them in descending order of the number of evens. So I start with EEE, 3 evens. The next 3 outcomes all have 2 evens. The next 3 all have 1. And finally, at the end, I have no evens. It may not seem like it, but that does make it easier to calculate probabilities. If I then define the event A that I'm getting at least 2 evens, look how easy this is. All I need to do is look at the top row where I have either 2 or 3 evens. And so A is, you can see listed there, consists of EE, EO, EEO, EOE, and OEE. And because, again, when you roll the die, evens and odds are equally likely. In this case, all 8 of these are equally likely to occur. Each one individually has a probability of 1/8. So we can calculate the probability of A by adding up the probabilities of triple E, EEO, EOE, OEE, but because these are all equally likely, all we have to do is count up how many elements are in A and divide that by the number of elements in the sample space, which is 1/2. Okay, or another way to look at it is that 4 out of 8 belong to A. Since we're all equally likely, the probability must be 4/8 or just 1/2. All right, does that make sense? All right, now we're going to switch our gears a little bit and create a new experiment where the outcomes are not all equally likely. We're going to see how that changes everything. All right, now imagine we're playing a game, but this is not with standard dice. These dice are a little bit different. Each of these each of these dice contains the numbers 1, 3, 5, 7, 2, 4. Okay, so we don't know why, but let's just say this game is a very bizarre set of dice. There's no 6, there's a 7. And so therefore, the chances of getting an even, instead of being 1/2, is 4 out of 6, which is 2/3. And therefore the odds of getting, or the probability of getting an odd number is 2 out of 6, which is 1/3. Interesting. So what does that do to the probability of getting 2 evens, or EO, or OE, or OO? Okay, so in the next slide, all of the possibilities are listed. Okay, so let me give you a minute to catch up and I'll show you the list. And you'll see that all of a sudden, these 4 outcomes are not equally likely. Oh, sorry, wait, hold on. I'm not sure if you were ready or not. All right, I think you're good. All right, let me show you how that would work with 2 rolls. So what you're going to do, now remember, the probability of getting an even is 1/3, and the probability of getting an odd is 2/3. So to get the probability of 2 evens in a row, you just multiply the probability of an even by the probability of even, or 1/3 times 1/3, which is a 9th. Okay, so this is, you're just multiplying these together. Here you're doing this. Here you're doing this. Oops. And so you're literally just multiplying them together. And so now these 4 outcomes, EE, EO, OE, and OO, all of a sudden they're not all the same, are they? No, EE is 1/9, OO is 4/9. EO and OE are each 2/9. Aha. So now we're going to reintroduce that last event we had, F, which means at most 1 even number turns up. And we're going to calculate its probability. Oh, sorry, I'm sure, let me give you a minute to catch up again. All right. So let's go back and revisit the same problem. F is the event that at most 1 even number turns up, or in other words, EO, OE, and OO. Now, because they're not all equally likely, we cannot calculate this as simply the number of elements in F over the number of elements in the entire sample space. Let me write it like this. Instead, we're going to write down the individual probabilities, which we saw in the previous slide. EO and OE are 2/9 each. OO is 4/9. So when you add those up, you end up with 8/9, as opposed to 3/4, which we found when they were all equally likely. So all of a sudden, that probability is now 8/9, and you must do that by adding the individual probabilities together. So this is the most general approach. This will work all the time. This approach in the box here, by counting the elements, this only works again in the special case where each element is equally likely. You should never assume that, by the way, unless you know that is true for a fact. All right, so what we're going to do now is introduce some rules for more complex situations. Sometimes they're called compound probabilities. In these cases we looked at so far, we were basically just taking an event based on the sample space, which is fine. But what happens if we're interested in the probability of, let's say, 2 different events occurring at the same time? Well, we need these rules to deal with more complicated situations. All right, so what do I mean by that? Well, some of the set theoretic concepts we saw earlier will be very useful in this next discussion. So the first thing we note is that there's 3 basic rules that we want to introduce. We have the addition rule, the complement rule, and the multiplication rule. Each one applies to a different situation. And so what we're going to do is go through them all and understand where they're coming from and how to use them and what they're actually telling us. Okay, so the only thing we still have to do, there's more background we need, but already we understand how to do the addition rule, or it'll be very straightforward. The complement rule, well, we have to introduce the concept of complements, and then for the multiplication rule, we have to take a bit of a detour and introduce some new types of probabilities that we have not yet encountered. All right, but I think you'll find this to be very straightforward. All right, so let's start with the addition rule. Now, the addition rule applies to cases where we're taking the probability of a union of events. All right, so you can see that what we're doing is we're taking a union of A and B and calculating the probability of that union. And so it's formally defined as the sum of the probability of A plus the probability of B. But then we have to subtract the probability of A and B. Now you're probably thinking, well, that doesn't make any sense. Why don't we just add up the probabilities of A and B? Well, there's a good reason for that. I'm going to show it to you with our friend, the Venn diagram. And you'll see why this thing is so useful. All right, so before we do any actual examples, let me show you why we need to subtract the piece in the middle. All right, so first, let me add a new slide in here. And let's just say we have events A and B. All right, now clearly this is the intersection between A and B. Now, what I'd like to do here is introduce a new notation. I'm going to define section 1 as everything in A that does not overlap with B. Section 2 will be, actually, let me do that in a different color. Just to make it easier to read it. And then section 2 is the intersection between the two. And section 3 is the area in B that does not overlap with A. So we could think that of this as A union B equals the sum of areas 1 plus 2 plus 3. Those areas have been defined to make sure there's no overlapping. So clearly the union equals 1 plus 2 plus 3. Now, A by itself equals 1 plus 2. B by itself equals 2 plus 3. Now, what if I tried to calculate the union of A and B as the probability of A and B, and I did not subtract the overlapping part? Well, here's the problem. A plus B equals 1 plus 2 plus 2 plus 3. Let's try that again. A plus B could be thought of as 1, 2, 2, and 3, which does not equal, as we saw on the top, 1 plus 2 plus 3. In other words, just by combining A and B directly, without subtracting the intersection, means double counting section 2. All right. So in other words, if the reason why up here we need this piece is because if we don't subtract that, what you're effectively doing there is you're subtracting the 2. So therefore, this is the equivalent of saying 1 plus 2 plus 2 plus 3 minus 2, which leaves us with what we need, which is 1 plus 2 plus 3. All right, you don't have to memorize this. Nobody's going to test you on this, but I just want you to see why this piece is necessary. It prevents us from double counting the intersection in the middle. If you forget about that, the probability will be too high. All right, I just thought you'd find that interesting. So this is the rule. So let's do an example of this. Okay, what do we have here? Here we go. So we're back to the die rolling experiment. And we have 2 events defined in that experiment. The first roll is even, which means either we got EE or EO. And exactly 1 roll is odd, which means we either got OE or EO. So what do we want to know? We're going to ask ourselves the following question. what's the probability that the first roll is odd, which is A, even rather, or exactly one roll is odd, B. So in other words, this question is, what's the probability of A union B? Okay, so we're being asked, what is the probability of A or B taking place? Okay. All right, well, now we're going to apply the rule. So we remind ourselves that A contains the elements EE and EO, B contains the elements EO and OE. The intersection between them is actually this element EO. They do overlap. In fact, let's see if I can squeeze this in here. I'm going to do the Venn diagram in a very interesting way. I'm actually going to show these points. That way you can see that those three elements are in the union, but the EO is in the intersection. So I need to calculate the probability of this shaded region. Okay, and here's of course the intersection between them, which is our EO. So we're going to apply the rule that we just learned. But before we do that, remember, in this case, the sample space has all elements that are equally likely. That implies that the probability of A is 1/2, 2/4, or 1/2. The probability of B is 2/4 or 1/2. The probability of A intersect B is 1/4. End of story. Because they're all equally likely, I can easily do it this way. In other words, you know what I've done? I've taken the number of elements in A and divided by the size of the sample space. Now I'm ready to plug these in to the formula. Okay. And let's see. Hold on 1 second. All right, and so when we do this, let's see what happens. All right. There we go. So we plug them in, and we do in fact end up with 3/4. Now, I'm going to show you in a second a way that we can confirm that we've done this correctly. But first, let's just note that we've used the addition rule, and we were careful to subtract the overlapping part between the two sets and come up with the correct answer, which is 3/4. Now, in this case, there's another approach we could have actually taken. Just a quick reminder, A contains EE and EO. B contains EO and OE. The union of these two events is EE, EO, and OE. And again, with the sample space with equally likely outcomes, what we could have done as an alternative is to count how many elements are in the union and divide by the number of elements in the sample space. Oh yeah, it's the same thing. So that means we must have done it correctly when we used the addition rule. So either way, it's going to be 3/4. And that's always good to know. We've proven that we must have done it correctly. All right. Now, of course, in all these cases, if you are going to, on a test, be asked, what is the probability of A union B? You can do it whatever way you want. There's almost always multiple ways of doing anything in math. And, unless it's specifically asked for one technique, you can always do the one that makes the most sense to you or is the quickest. So here is no exception. There's at least 2 different ways of doing this. And you can use them as double checks for each other, or else you can just simply say, well, I like this approach better. And then you can do it that way. All right. Now, here's an interesting question. What happens if A and B are mutually exclusive? Does that change anything? Well, not exactly. What it does is it simplifies. It doesn't change the approach, but it simplifies our results. Because what happens here is that when you have mutually exclusive events like this, A and B, if A and B equals the empty set, this implies that the probability of A and B is 0. And 0, any event that has a probability of 0 is said to be the impossible event. So if the probability of A is equal to 0, A is said to be an impossible event. So just a quick example, if A represents all the even numbers and B is the odd numbers, the probability that a number is both even and odd is 0, because that can't happen. So when you see two mutually exclusive events like this, the probability of them both being true is equal to 0 because they have no elements in common. All right, so again, we think of this as an impossible event. Well, what does that have to do with the addition rule? Well, all right, and here it is. The probability of the empty set is 0. Just in general, the empty set has a probability of 0, or any event that is the empty set. So what does that have to do with the addition rule? Well, you recall the addition rule requires us to subtract the probability of A intersect B. But if that probability is 0, then we don't need to worry about it. Okay, so there is the full addition rule, or the general, I guess I should call it the general addition rule. Which we just got through using, is that the probability of A union B is the probability of A plus the probability of B minus the intersection. But when A and B are mutually exclusive, the probability of A intersect B is 0. So we end up with this. Okay, in other words, notice what's happened. We simply got rid of that intersection because it has a probability of 0. And what's left is the so-called simplified addition rule. And it just makes things a tiny bit. It's not that big of a time saver, but it just means that when we're dealing with mutually exclusive events, the addition rule becomes very simple. And in fact, remember, in using Venn diagrams, if you think of this as regions 1 and 2, it's just 1 plus 2. So there's no need to subtract the intersection because it doesn't exist. So the probability A union B and that's it, we're done. All right, let's look at an example of that. Sorry. So when they don't overlap, you can see these two, there's nothing in between. So therefore there's no double counting involved. We just add them up and that's the end of it. All right, let's look at an example of this. Now, same thing, same sample space. A is the first roll is even. That is the events E, E, and EO. And now B is the event that the first roll is odd, OE, OO. And you notice right away that the two have nothing in common. They're mutually exclusive. Because the first roll can't be both even and odd, obviously. Which means that we can use, if we are trying to calculate the union of these two events, we can now feel free to use the simplified version of the addition rule. So what we'll do is we'll go ahead and calculate the individual probabilities first, and then we'll combine them into the addition rule, the special addition rule, that is. All right, here we go. So clearly, and again, given that these are all equally likely events in the sample space, A must have a probability of a half, or 2/4. B must have a probability of a half as well, or 2/4. Okay, so therefore, when we plug these in, and you notice there's no intersection, you could add this if you want to. And so when you plug these in, you end up, in this case, with 1. Now you can see why it has to be 1, because one of those two events has to be true with certainty. And in fact, when we have any event A whose probability is 1, we say that A is a certain event. You might recall if it was 0, oh, wait, what did I do? Then we call that impossible. It's just a quick overview here. Okay. I shall be consistent here. So a probability of 1 means something is guaranteed to happen, and probability of 0 means it's guaranteed not to happen. So here, this makes perfect sense because either the first roll has to be odd or it has to be even. There's no other possibilities out there. And since there's no overlapping between them, we don't need to subtract the intersection because it doesn't exist. All right. So now that's pretty much all we need to say about the addition rule. I think you'll agree that it's pretty straightforward. All right, now the second of the three on our list go back for a second, is the complement rule. The complement rule is probably the easiest of them all, but we also have to sort of take a detour and remind ourselves or introduce to ourselves the concept of complements in set theory. So what exactly does it mean for events to be complements? Well, I'll show you the formal definition and then I'll show you some examples. Two things must be true for A and B to be complements. First of all, their union must equal the entire sample space and their intersection must be empty. And this implies that the probability of the union is 1 and that the probability of their intersection is 0, which in turn means that A union B is a certain event and that A intersect B is an impossible event. So you're probably wondering, well, what, I can't imagine anything in the real world that would work like this. Well, there's actually lots of good examples. Once you get the hang of it, you can think of any number of examples you want. So let me show you a good example of this. And again, it involves our old friend, the games of chance. The deck of cards, for example. So I would say, like, suppose that an experiment consists of choosing a card from a deck. Now, just as in case you have forgotten how cards work, a standard deck of cards contains 52 cards divided into 4 suits, which are spades, clubs, hearts, and diamonds. Now, among these, the first 2 are black. And these are red. There's 13 cards within each suit. Now, we don't really need that information for this particular example, but it may come up later on in some of the problem sets. So we can take each suit and break it down into 13 cards. Okay, so each suit contains 13 cards, each with a rank, they're called ranks, that reflects its value, I guess you could call it. Now we have the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, J. Now these last 3 are the picture or face cards. J is the jack, Q is the queen, and K is the king. And by the way, in most games, the ace is the highest, but I'm just listing them all out for you. So with 13 cards in each suit and 4 suits, altogether there are 52 cards, half of which are red and half of which are black. Okay, that's all we need to know for now. So therefore, suppose that I conduct this experiment. So once again, a card is chosen from a deck. The sample space is the entire deck. And we know that each of the cards is equally likely to be chosen. So this is like the die rolling experiment where each outcome is equally likely. And so if I wanted to know, for example, the chances of getting a particular set of cards, it's very easy because I can just count the number of cards that qualify and divide by 52. So the sample space, I won't bother to write it all out. The sample space is the deck. Suppose we define the following events. A is the event. The card is red. And B is the event that the card is black. Now, here's what we want to know. Now remember, we're trying to figure out, let me just throw this in here. Are these events complements? Now, how do you know? Yes or no? I mean, you've got to prove it. So remember how that works. Their union must be the entire sample space. And their intersection must be empty. So let's look at the first one. Are A and B mutually exclusive? Oops. The answer is yes. No card can be both red and black. It doesn't exist. That question is satisfied. I'll put a big check mark here. Are the union, or does the union equal the entire sample space? I'll just put equals S. Yes, because all the cards are either red or black. And so that's a big yes as well. So that tells me our logical conclusion from all of this is that the two events A and B are complements of each other. Okay, so in other words, this proves that A and B are complements. All right, so the red and the black cards are complements. Now, let me ask you this question. And based on the same reasoning, suppose that the experiment is not picking cards from a deck, but instead we're going to a piece off of a chessboard. A is the event that the piece is white. B is the event that the piece is black. Are A and B complements? I guess this is bad English up here. This is fine. It was giving me an eyebrow there, a raised eyebrow. Are you sure you wanted to say that? Picking a piece off a chessboard, I guess that'll do. So the question is, are these complements? Well, let's think about it in two ways. We need to know two things. Let's see. Let me write it like this. Okay, so A union B equals the empty set because no piece can be both white and black. Oh, that one's a yes. So yeah, I forgot to write in the yes. On the other hand, what about the union? Yes, all pieces must be white or black. That's a big yes. So therefore, the answer is the white and black pieces are complements. All right, let's just do one more example. This time we're picking cards from the deck, but the events are different. Suppose an experiment consists of choosing a card from a deck. So we define the event. A is the card is a heart. And B is the event that the card is a club. Are A and B complements? Well, let's find out. Now, I'm sure, I mean, if you play cards, you know already that the answer is no, but let's see why. So we'll just ask ourselves the same questions that we've been asking all along. Is the intersection empty, or are they mutually exclusive? So the first one, the answer is yes, because no card can be both a heart and a club. But what about the second one? No, because not every card is either a heart or a club. In other words, we're leaving out the spades and the diamonds. So that means that A and B in this case are not complements, because their union does not represent the entire sample space. In other words, when I combine those two sets of cards, I do not have the full deck. And therefore, these are not complements. So I cannot use the complement rule on them. That's what this is all about. Can I or can I not use the complement rule? Now, the complement rule couldn't be any simpler. The rule itself is very, very easy. I just want to show you, though, that we're going to introduce some new notation here. Going forward, we're going to use the letters. Oh, by the way, let me just leave this for a second in case you're not done. We're going to use a special notation to represent complements. And it's a very simple notation, all right? We're going to write a complement is AC. Okay, so this is A. AC is a complement. Okay, it just makes it easier in our expressions. Now, with all that being said, watch how simple this thing is. It can be written in two equivalent ways. the probability of A equals 1 minus the probability of A complement, and probability of A complement equals 1 minus the probability of A. All right, now here's an interesting question. Why? Why does this rule hold? All right, I'm going to show you. So we know that for events A and A complement, two things must be true. All right, this tells me that their intersection is empty and their union is the entire sample space. So if I try to apply the addition rule to these events, that would be what it would look like. Now, we can simplify this because this piece is equal to 0. So we can rewrite this as the probability of A union A complement is the probability of A plus the probability of A complement. So what does that get us? All right, let me move this on to the next slide. Because we know one more important thing. Yeah, I'll just handwrite it in here. Since A union A complement is the entire sample space, the probability of A union A complement is 1, and therefore this expression can be written as 1 equals PA plus PC, PAC. And that tells me that either one of two things is true algebraically. Both of these are true. And there we go. So basically, we proved it by using the properties of complements and combining them with the addition rule. And so this is the result. Now, you don't have to do this. I just want you to see why this rule works. It's always more, you're always going to understand something better when you've seen why something is true rather than just being told to memorize it. That's my opinion. Well, now it's time to do some examples. Actually, it looks like, ooh, it's already 10 o'clock. I'll tell you what, let's save the examples for after the break. And then before we dive into the next rule, which is the very complicated multiplication rule, what I would like to do is start showing you some of those cool videos that I mentioned. And so we'll do that. When we get back, we'll finish up our examples of the complement rule. We'll watch some videos, and then we'll introduce the multiplication rule, which is by far the most complicated of the three. Okay, so all right, so we'll stop here, And when we get back, we'll have all this good stuff to look forward to. All right. So see you in a little while.
Excuse me.
Oh, yes, go ahead.
Can you check if you got it?
Oh, yes. I forgot all about that. Yeah.
No, you're
Um,
good. I just want to make sure you get it so I get my points worth.
I
you what mean?
know. Well, I want to
It's
give you your points too. I just.
I honestly don't know what's going on. I never honestly had like an issue like this.
John Pillsbury?
Yeah, that's me.
Right, there it is. All right. It arrived like an hour late, but it's there.
Hey, man, as long as you got, if you do you want me to send you the show my work part, where I prove how I got my answer? Like,
Sure. If you have it, go ahead.
no, I have it. I'm gonna send it right in that email list. Like, when I make a chain of, you know what I mean?
Yeah. Okay. Go ahead. Sure.
Okay.
That's fine.
I'm sorry. I just want to make sure you got it. That's all.
You did the right thing.
Thank you.
Okay. All right. So now we're ready for examples of the complement rule. All right, so first of all, let's go back to our favorite example, the die rolling experiment, where again, the sample space is EE, EO, OE, and OO. So here we have the events, the second roll is even, EE, OE, and then we have the second roll is odd, EO, OO. So when you look at those events, you'll notice a couple of interesting things. First of all, it's on the next slide. Okay, good. So if you notice, if you try to take the union of A and B, you're going to get back the entire sample space. But on the other hand, the two events are mutually exclusive. I'm going to put that in there again, meaning that their intersection is the empty set. So right off the bat, we know that A and B are complements, or what we could do is write B as a complement. So if that happens, then what we can do is apply the complement rule in the following way. So first things first, each of these individually has a probability of a half. Because again, remember, with this sample space, all the outcomes are equally likely. So we just count them up. This one is 2/4 or a half. And for B, we have the same thing. And also, we can write B as a complement. So therefore, we can conclude this by saying P of A is a half, P of A complement is a half. And you'll see that that ties in nicely with both versions of the complement rule. So in other words, if we write out both of them, now remember there were two of them, the probability of A is 1 minus the probability of A complement, and the probability of A complement is 1 minus the probability of A. So on the next slide, we're going to plug in these numbers and show that these both are true. All right, let's do it. So here's the first case. And the probability of A is a half. So 1 minus 1/2 is 1/2. All right, in other words, 1 minus the probability of A complement is 1 minus a half, which is a half, which in turn equals A. And here, the probability of A complement equals 1 minus the probability of A, or 1 minus 1/2 equals a half. So both of these conditions have been met. And that's, of course, what we would expect because we've proven that A and A complement are, in fact, complements. It can't work out any other way. All right, now let's make up a new example here. Something completely different, something that doesn't involve dice. How about that? Let's try this. So let's just say this. Suppose that in a class of 25 students, 15 are commuters and 10 live on campus. So the sample space is the entire set of 25 students. And let's just define A to be the event that we imagine this, the experiment consists of randomly picking a student from this class. And A is the event that the student chosen is a commuter. Okay. And B would be the event, of course, that the student chosen lives on campus. So the first thing we want to ask ourselves, because clearly we're talking about the complement rule here, is we'd like to know, are A and B complements? Okay, so in other words, based on the way we've defined everything, does it make sense that A and B are complements? All right, well, of course, in order to answer this question, we have to show the two conditions that are required for two events to be complements. So in other words, what we're basically saying is that, is it true that the union is the entire sample space? And is it also true that the intersection is empty? That's what we need to prove whether or not they're complements. All right, well, I mean, I think it's pretty clear. It's a very simple example, but let's just go through and demonstrate whether this is true or not. So is A union B equal to the entire sample space? Yes, because all the students either commute or live on campus. There's no third category. All right, that one's a done deal. Now, how about this one? How about the overlapping? Is it possible that they're mutually exclusive? So is A intersect B equal to the empty set? And the answer is yes again, because no student is both a commuter and lives on campus. It's one or the other. Now, of course, obviously, if you have a room at school, that doesn't mean you don't stay at home once in a while, but you're one of two categories. You're either paying for a room or you're not. Let's put it that way. So what we've just done is demonstrated that A and B are complements. So we know that that's true. Because again, there's no overlapping between the two groups, but the two groups cover all the students. So A and B are complements. Using the complement rule, what is the probability of A and what is the probability of B? All right, so now keep in mind that B can be rewritten as a complement because we know that they're complements. We just got through proving it. All right, so we're going to use our rules. But before we do that, it would be nice if we knew the probability of A by itself and the probability of B by itself. So remember the way we define these. Let me just grab these again. And if you recall, 15 are commuters and 10 are living on campus. So that means out of a class of 25, TA is 15 out of 25, which is 0.40. No, wait, no, it's not. Hold on, sorry. 15 out of 25 is 0.60. Now, but by the way, we're implicitly assuming that everybody in the class is equally likely to be chosen. So if I randomly pick a student from this group, the probability I've chosen a commuter is 15 out of 25 or 0.60. Since there are 10 who live on campus, the probability of B, which is the same as the probability, we'll call that a complement, is 10 out of 25 or 0.40. All right, so what we're basically going to do is show that the complement rule works in these cases. All right. And by the way, in a lot of cases, you will not necessarily know what's in, or let's just say that you might be given different kinds of information. So in this case, we don't really have to use the complement rule. We can figure it out for ourselves because it's simple and straightforward. But in some cases, doing that would be very, very complicated. Let's say that the sample space is really huge and the outcomes are not equally likely. Then in that case, you're probably going to be better off using the complement rule than simple counting. But it's good to know that there's two different ways of getting at the same results. So what we're going to see is that, of course, the complement rule has to hold both versions of it. All right, so remember, the probability of A, we already figured out is 0.60. And the probability of A complement is 0.40. So either way, we get the right answer. All right. So the complement rule is very straightforward. Now, the third of the final rules that we will be defining, the multiplication rule, is a very complex idea. And so that will require a lot of background in order for us to fully understand it. So I think this is as good a time as any to start showing some videos. So let me go look at the list. And let's see. Where is Moodle? Here we go. All right, so I got a bunch of cool videos here. Now we've already seen, I think the last one we saw was the lady tasting tea. Is that the right one? I think that was it. I'm pretty sure we left off with the lady tasting tea. So what we're going to do is look at a video called Probability Part 1. And it's basically an overview of what we've been doing throughout Chapter 11. But it's a very good video. It's very helpful to help us visualize exactly what's going on with probability theory. So let's start with this one. Let me just send that over to you, as always. I'll put it in the chat room. Hold on one second. And let's check it out.
IoT product is no easy feat. You need a solution that works out of the box, and you won't call in sick today, like whether or not you're going to catch all the red light. Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. If you've ever seen a face in an onion or a grilled cheese or any other inanimate object, you've experienced pareidolia, which is a product of our brains that causes us to see the pattern of a face in non-face objects. This happens because our brains are so good at seeing patterns that they sometimes see them when they're not really there, like a face in this bell pepper. And faces aren't the only patterns we see. Our brains recognize patterns in everything, especially in sequences of events, like the kind we're going to talk about today as we start talking about probability. All right, first, let's just establish a more specific definition of what probability is, because the way we use the word in everyday life can be different from how we use it in statistics. Statisticians talk about two types of probability, empirical and theoretical. Empirical probability is something we observe in actual data, like the ratio of girls in each individual family. It has some uncertainty because, like the samples in experiments, it's just a small amount of the data that's available. Empirical probability probabilities, like sample statistics, give us a glimpse at the true theoretical probability, but they won't always be equal to it because of the uncertainty and randomness of any sample. The theoretical probability, on the other hand, is more of an ideal or truth out there that we can't directly see. Just like we use samples of data to guess what the true mean or standard deviation of the population is, we can use a sample of data to guess what the true probability of an event is. Say you play a slot machine over and over and over and over and over and over. You'll be able to guess the probability of winning the jackpot by counting the number of times you win and dividing it by the number of times you played. If you play 100 times and win 6 times, you can be pretty sure that the probability of getting a jackpot is around 6 out of 100 or 6%. Now, this isn't to say that you can rule out the true probability is 5% or even 10%, but you're relatively sure that it's close to 6% and not, say, 99%. So the empirical probability can be a good estimation of the theoretical one, even if it's not exact. So far, we've been talking about the probability of just one event, but often there may be 2 or more events that we want to consider. Like, what if you want to know the probability of picking a purple or a red Skittle from a bag? The proportion of each color in a bag of Skittles is roughly equal, 20% for each of the 5 colors. So let's say you randomly select a Skittle without looking. For this, we need the addition rule of probability. Since a Skittle can't be 2 different colors at once, the color possibilities are mutually exclusive. That means the probability of a Skittle being red and purple at the same time is 0. So we can use the simplified addition rule, which says that the probability of getting a red or purple Skittle is the sum of the probability of getting a red and the probability of getting a purple. Since we're going to be talking a lot about probability in the next few episodes, I'm going to introduce a little notation. Instead of writing out the probability of red, we can use the notation P of red. The probability of getting a red or purple would be written P of red or purple. So far, we know what the probability of red or purple is. It's P of red plus P of purple, or 0.2 plus 0.2. That equals 0.4, or 40%. I like all Skittles, so the probability I will get a Skittle I like is 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2. That's 100%. Good odds. Red and purple Skittles are mutually exclusive, but not all the events we're interested in are. For example, if you roll a die and flip a coin, the probability of getting tails is not mutually exclusive of rolling a 6, since you can both roll a 6 and flip tails in the same turn. Since P of tails or 6 is not equal to 0, these 2 events are not mutually exclusive, and we'll need to adjust our addition rule accordingly. The full version of the addition rule states that P of tails or 6 equals P of tails plus P of 6 minus P of tails and 6. When 2 things are mutually exclusive, the probability that they happen together is 0. So we ignored it. But now the probability of both these things happening is not 0. So we need to calculate it. You can see here there are 12 possible outcomes when flipping a coin and rolling a die. There are 6 outcomes with tails and 2 outcomes with a 6. If we add all of those together, we get 8. But by looking through the chart, we can tell there are only 7 possible outcomes that have either tails or a 6. When we count tails and 6s independently, we double count the outcomes that have both. If we didn't subtract off the probabilities of tails and 6, we would double count it. Let's put these probabilities into a Venn diagram, and we can see even more clearly why we need to subtract P of tails and 6. If this circle is all the times we flip tails and the other circle is all the times we roll a 6, the overlapping area is counted twice if we simply added the 2 circles together. In this simple case, we could easily see what the probability of tails and 6 is, but sometimes it's not so easy to figure out. That's why we have the multiplication rule, which helps us figure out the probability of 2 or more things happening at the same time. Let's say you just found out that actor Cole Sprouse goes to your local IHOP pretty often, and there's a 20% chance he'll be there for dinner any given night. And yeah, I know that's not how people work, but we're going to say that that's how Cole Sprouse works. Anyway, to top that off, your local IHOP has a promotion where they randomly select certain nights to be free ice cream nights, in the hopes that customers will keep coming back in case that night is the night. Each night, there's a 10% chance that it will be free ice cream night. Now, you love ice cream, and you like Cole Sprouse, as do we all, and your perfect night would include them both. So you try to calculate the probability that will happen on your visit tonight. Using the multiplication rule, multiply the probability that Cole Sprouse will be at the IHOP. 0.2 with the probability that it will be free ice cream night, 0.1, And you come to the sad realization, there's only a 2% chance that you'll get to see Cole and get free dessert tonight. When we want to know the probability of two things happening at the same time, we first need to look at only the times when one thing, Cole Sprouse at IHOP, is true, which is 20% of the time. Now that we reduced our options to just Cole nights, out of all of those Cole times, how often is it free ice cream time? Only 10% of Cole nights. 10% of the original 20% leaves only a 2% chance that both will happen at the same time. But you can always change your expectations and calculate the probability of getting either by using the addition rule, Cole or free ice cream, which is calculated by adding the probability of Cole to the probability of free ice cream minus the probability of both, so we don't double count anything. You realize there's a 28% chance that something good will happen tonight. So you decide to go. No matter what, you're gonna get French toast. Cole Sprouse and free ice cream night are independent. Cole doesn't have any secret knowledge about when it's free ice cream night, so it has never affected his decision to come. Two events are considered independent if the probability of one event occurring is not changed by whether or not the second event occurred. In more concrete terms, if Cole's decision to go to IHOP is independent of IHOP's decision to give out free ice cream, then the probability of Cole showing up should be the same on both ice cream and non-ice cream nights, since he's just choosing randomly. We write conditional probabilities as P of event 1 given event 2. Conditional probabilities tell us the probability of event 1, given that event 2 has already happened. If two events are independent, like Cole and ice cream night, then we expect P of Cole given ice cream night to be the same as just plain old P of Cole, since the two things are unrelated. If P of Cole given ice cream wasn't the same as plain old P of Cole, that means that ice cream night might somehow affect Cole's decision to show up at IHOP. We calculate conditional probability, P of event 2 given event 1, by dividing the probability of event 1 and event 2 by the probability of event 1. The role of conditional probabilities are particularly important when we consider medical screenings. For example, when screening for cervical cancer, it used to be recommended that all adult women get screened once a year. But sometimes the results of the screenings are wrong. Either they can say there's something abnormal when there isn't, that's called a false positive, or that everything is all clear when it's really not, called a false negative. This is exactly the kind of scenario where knowing the likelihood that something is actually abnormal, in this case cervical cancer, given that you've gotten positive test results, would be useful. That is P of cancer given positive test. When looking at the data of people who don't have cancer, 3% will get a false positive, and people who do have cancer will get false negatives 46% of the time. This means we miss a lot and maybe freak some people out who don't need to be freaked out. The logic of conditional probabilities can help us make sense of why doctors have recently recommended that these tests be done less frequently in some cases. In the United States, the rate of cervical cancer is about 0.0081%. So only about 8 in 100,000 women get cervical cancer. Using our rates of false negatives and positives, we can see that for every 100,000 women in the US, only about 4, and we are rounding here, of the about 3,004 people with positive tests actually had abnormal growth. That means the conditional probability of having cancer, given that you've got a positive test, is only 0.1%, give or take, we're rounding. And these positive tests require expensive and invasive follow-up tests. And I want to point out here that conditional probabilities aren't reciprocal. That is to say, P of cancer given positive test isn't the same as P of positive test given cancer. That's about 50%. In real life, you're not always going to know the probability of Cole Sprouse showing up at the IHOP. He's more unpredictable than I gave him credit for. Unpredictable like pretty much the rest of life. It can be really difficult to put a specific probability on a lot of everyday situations, like how likely it is that your teacher will call in sick today, like whether or not you're going to catch all the red lights on your way to school. Probabilities can, as we've seen, require a lot of calculations, and there's not always time for that. But that doesn't mean they belong only on the school side of your brain. Say you want to go out on Friday night with friends. More than anything, you don't want it to suck. Last week, you wound up on the couch watching Sandy Wexler again. You know it'll be hard to get tickets to see Black Panther, so you make a backup plan, just in case. You can always stream Get Out without stealing it, of course. But if you're determined to see Black Panther in the theater, probability will help you set your expectations. If you'll only settle for center row tickets, you're more likely to be disappointed. Your chance of seeing Black Panther is going to be greater if you're willing to settle for whatever tickets you can get. Probabilities help us understand why it makes sense to apply to more than one college, why you shouldn't expect that the first short story you write will get an A and be published in the New Yorker, and how likely it is that you'll get mono, given your significant other has mono. Probability can help you figure out that too. Thanks for watching. We'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Imig studio in Indianapolis, Indiana, and it's made with the help of all these nice people. Our animation team is Thought Cafe. If you'd like to keep Crash Course free for everyone forever, you can support the series at Patreon, a crowdfunding platform that allows you to support the content you love. Thank you to all our patrons for your continued support. Crash Course is a production of Complexly. If you like content designed to get you thinking, check out some of our other channels at
Mhm. Well, I must say some of those examples were a little bizarre. And also some of that material we haven't gotten to yet. She did start talking about the multiplication rule at some point, which we're going to do in a few minutes. So if that went over your head, that's fine because we haven't gotten to that point yet. But yeah, this company usually makes pretty good videos. I think that what they have to do is avoid having such obscure references. I have no idea who Cole Sprouse is. Do you? That means nothing to me. So I think they need to be careful about that. But other than that, usually these videos are pretty good, especially because the graphics are so much fun. So now there's one more video I want you to see. Now this one is based on combinatorics, and it's just a fun video. It's a very surprising video too, because, well, I don't want to spoil the surprise. Let me show you what they're going to be talking about, but it totally is based on everything we did in our discussion about combinatorics, but yet it refers to a very interesting question or problem that you might run into in the real world. So we'll see that one, and then we'll get back to the multiplication rule. All right, hold on one second. Let's see. Oh, it's, here it is. Yes.
Embed a Sisense dashboard into your site.
All right, let me fire that off to you. And this one is really well done, very well done. Okay, here we go.
Site or app in 3 simple steps. First,
imagine a group of people. How big do you think the group would have to be before there's more than a 50% chance that 2 people in the group have the same birthday? Assume for the sake of argument that there are no twins, that every birthday is equally likely, and ignore leap years. Take a moment to think about it. The answer may seem surprisingly low. In a group of 23 people, there's a 50.73% chance that 2 people will share the same birthday. But with 365 days in a year, how is it possible that you need such a small group to get even odds of a shared birthday? Why is our intuition so wrong? To figure out the answer, let's look at one way a mathematician might calculate the odds of a birthday match. We can use a field of mathematics known as combinatorics, which deals with the likelihoods of different combinations. The first step is to flip the problem. Trying to calculate the odds of a match directly is challenging because there are many ways you could get a birthday match in a group. Instead, it's easier to calculate the odds that everyone's birthday is different. How does that help? Either there's a birthday match in the group or there isn't. So the odds of a match and the odds of no match must add up to 100%. That means we can find the probability of a match by subtracting the probability of no match from 100. To calculate the odds of no match, start small. Calculate the odds that just one pair of people have different birthdays. One day of the year will be person A's birthday, which leaves only 364 possible birthdays for person B. The probability of different birthdays for A and B, or any pair of people, is 364 out of 365, about 0.997, or 99.7%, pretty high. Bring in person C. The probability that she has a unique birthday in this small group is 363 out of 365, because there are 2 birth dates already accounted for by A and B. D's odds will be 362 out of 365, and so on, all the way down to W's odds of 343 out of 365. Multiply all of those terms together, and you'll get the probability that no one shares a birthday. This works out to 0.4927. So there's a 49.27% chance that no one in the group of 23 people shares a birthday. When we subtract that from 100, we get a 50.73% chance of at least one birthday match, better than even odds. The key to such a high probability of a match in a relatively small group is the surprisingly large number of possible pairs. As a group grows, the number of possible combinations gets bigger much faster. A group of 5 people has 10 possible pairs. Each of the 5 people can be paired with any of the other 4. Half of those combinations are redundant because pairing person A with person B is the same as pairing B with A, so we divide by 2. By the same reasoning, a group of 10 people has 45 pairs, and a group of 23 has 253. The number of pairs grows quadratically, meaning it's proportional to the square of the number of people in the group. Unfortunately, our brains are notoriously bad at intuitively grasping nonlinear functions. So it seems improbable at first that 23 people could produce 253 possible pairs. Once our brains accept that, the birthday problem makes more sense. Every one of those 253 pairs is a chance for a birthday match. For the same reason, in a group of 70 people, there are 2,415 possible pairs, and the probability that 2 people have the same birthday is more than 99.9%. The birthday problem is just one example where math can show that things that seem impossible, like the same person winning the lottery twice, actually aren't unlikely at all. Sometimes coincidences aren't as coincidental as they seem.
All right, that was kind of interesting. It was interesting the way they showed you how you can prove those results. The idea that you only need 23 people in a class to have a 50-50 chance that 2 of them have the same birthday is very surprising, given how many different birthdays obviously are possible. And so in the past, when I had all my classes in person, I would often, as an experiment, I would start asking people what their birthdays were. And I'd start writing them down on the board, and almost without fail, there'd be 2 with the same birthday. And even in a class with only 20 some odd people. And in fact, one year, the first 2 people that I called on had the same birthday. So that was kind of interesting. So yeah, it just shows you that combinatorics is a very powerful tool for calculating a lot of different results that you might not realize how useful it really can be. So anyway, now, the last part of this discussion is the multiplication rule, but we had to save it for last because it's the most complicated. All right, so this is the multiplication rule, and they did briefly mention this in the video, but now we want to take a step back and really define it properly. So the multiplication rule is used to calculate the probability of an intersection. Okay, so let me just mention that right up front. So the multiplication rule is used to calculate this type of probability, the probability of A and B, or A intersect B. Okay, this is the multiplication rule. If you recall, the union rule, the addition rule was defined on unions. So just a quick reminder, and of course the complement rule is defined on complements. But the multiplication rule is only meant for when we're trying to calculate the probability of two events occurring at the same time. Okay, and just as a point of notation, sometimes these are called joint probabilities because two things are jointly true. All right, so that's where we're headed. Now, in order to do this properly, though, we have to take a step back and introduce a very important example, which will help us define some of the new types of probabilities that we will need to understand the multiplication rule. All right, so first things first, what we're going to do is start with a table known as a joint probability table. And basically what it's going to do is take a set of data that is broken up into two different categories. The data that we see in this table will be defined as, in some cases, joint probabilities, and in other cases, we'll be looking at what are called either marginal or unconditional probabilities. So we'll explain those as we go along, but just remember, this table is designed to help us understand probabilities based on two different characteristics or categories. All right, now when you see the example, it'll make perfect sense. It sounds very abstract now, but once we start working with the example, I think you'll agree that it's really not that difficult, but we do have to go through it very carefully to make sure we really understand what's happening. All right, so let's jump ahead. Now, imagine that this is a school. This is not Purchase, obviously, but a college or a university that offers a business school. And within that business school, we're going to assume that all of the students are either getting a bachelor's degree. BBA stands for Bachelor of Business Administration, which means a college degree, of course. Whatever degree you're working on, most likely the degree that you'll be getting is a BA for Bachelor of Arts, but it could be a BS, which is a Bachelor of Science. And then maybe there's others that I don't know about, but those are the two standard ones. But here within a business school, we sometimes see these degrees called Bachelor of Business Administration. I'm not sure if there's any really hard or fast rules for what separates a BA from a BS anyway. I think they have a certain amount of leeway to choose those titles. MBA is called Master of Business Administration. Now, in order to be in an MBA program, you have to already have a college degree. This is what comes after college. It is often referred to as graduate school. Okay, you may have heard that word, graduate. The word's graduate school. It means you're taking a degree which is more advanced than a college degree. And one of the most popular ones is this MBA, because it means that you're probably going to be paid a lot of money when you're done with it. And so that's what that represents. And then we've got three majors: finance, accounting, and marketing. Now, one of the unfortunate things about this table is the lettering. We want to refer to different events throughout this section by the letter, which represents either what type of degree you're getting or what your major is. So you see what I mean in a second. B will represent BBA, M will be MBA, F will be a finance major, A is an accounting major, and then here's where the problem is. M is already taken, so we're going to use T for marketing. Okay, so just be aware of that. T is for marketing. And we're going to use these letters to help us calculate probabilities throughout this section. And so these numbers tell us how many people fall into these different categories. For example, this tells me that out of the total business school enrollment of 500, there are 130 students who are getting their bachelor's degrees in finance. Okay, how do I know? Because this is at the intersection of the row that contains the bachelor's degree students and the finance majors. And then, for example, here, I see that there are 35 MBA students who are majoring in accounting. Okay, so all of these up here tell me how many people fall into each category. On the bottom, we have totals, of course. So in other words, this 175 means altogether there are 175 finance majors between the bachelor students and the master students. This row total tells me that there are 400 bachelor's degree students and 100 MBA students. So it should be pretty straightforward what's going on in this table, but what we would like to be able to do with it is calculate some probabilities. So imagine a scenario where the business school has some, let's say they have an alumni magazine that they publish every so often. And for the next issue, they want to have on the cover a student from the current student body. And so somebody in this group will be chosen at random. Okay, and so we'd like to know different kinds of probabilities. For example, we can ask ourselves a question like this one. What is the probability that the student we chose is getting their bachelor's degree in finance? Or what is the probability that this student is getting their MBA in accounting? Or possibly it could be something like this. What is the probability that the student we chose is getting an MBA? Okay, so there's a lot of possibilities there. And we're assuming, of course, as usual, that all the choices are equally likely. We're randomly picking somebody out of this group. We've assigned a number to every student and we randomly pick a number. So like with a deck of cards, each person is equally likely to be chosen. And so we start by defining what's called a joint probability. So I mentioned that earlier. The probability that two events occur at the same time or are both true is known as a joint probability, meaning that two things are both true at the same time. Now, how can we figure these out? All right, well, let's look at some examples. Okay, but just be aware, joint probability means we've got an intersection, which means two different things are true at the same time. All right, so how about this? What if I want to know that, remember, we're picking a student at random. What if I actually do want to know the probability that this student I chose is getting their bachelor's degree in finance? Well, it's very simple because here's what we're actually doing. We find how many students are getting their bachelor's degree in finance, and then we find out how many students there are all together in the business school. And so this probability, which is written as the probability of B and F, is 130 over 500, or 26%. And it's really just that simple. And of course, remember, this is known as a joint probability because it means two different things are true at the same time. Getting a bachelor's degree, studying finance. So if I randomly pick somebody, there's a 26% chance that that person is getting their bachelor's degree in finance. Well, that doesn't seem too complicated, does it? No, it doesn't. All right. So what other possibilities are there? Well, let's try this one. Let me just fill it in here and then we'll grab the table. In fact, you know what I'm going to do? I'm going to copy this table onto a new slide. Yeah, it's going to be awkward if we have to keep rolling back and forth. So let me just copy it. Oh no, what happened? That was the name of that video. I'm telling you, it's this trackpad. There we go. All right. So with this table, now ignore the boldface. Actually, you know what? Let me go get the original one. Otherwise, you'll think the boldface means something. Hold on. Let's go back and get the original table with no bold facing. Except, I mean, for the totals, that is. And all right, that's the original table. So let's just pick another possibility. What if I want to know the probability that the randomly chosen student chosen is getting an MBA in accounting. In other words, the probability of M and A. So we look for all the students that are getting their MBAs in accounting right here and divide by the grand total. And that's going to be 7%. All right, so it's a small number. That's because accounting is a tough discipline, but those people will be paid very, very well. Okay, so any joint probability can be calculated in exactly the same way. Now, are there any other probabilities that we can derive from this table? Sure there are, but what are they? The next type of probability we want to introduce is called either marginal or unconditional probabilities. So what is this all about? This time we're interested only in probabilities for single events. All right, so let me show you an example of this. What if I want to know the probability that a randomly chosen student is getting their bachelor's degree? Now you notice I didn't mention their major. I just want to know the probability that they're getting their bachelor's degree. So we look ahead to the next slide, and you can see all together by adding up all of these students, I have 400 getting their bachelor's degree. The entire business program has 500 students. So therefore, this probability is very simply 400 out of 500, which is 0.8. And because we only have one event taking place, this is often known as an unconditional or marginal probability. Okay, so just, I don't want you to have to get stuck memorizing a bunch of stuff, but these words mean that we're simply looking at a single event, not two, just the one. And in this case, that would be getting a bachelor's degree. All right, now what if instead I'm interested in knowing somebody's major, just their major, not what level they're studying at, but just their major. For example, what if I just want to know the probability that the person that I chose is majoring in accounting? I don't care if it's a bachelor's student or an MBA student. I just want to know the likelihood that they're majoring in accounting. All right, well, let's look at the chart. The probability of A, just A, is 215 out of 500, which is 43%. And that's it. That's all there is to it. So these are easy too. You're probably wondering, well, where's the hard part? What's so challenging about this? Aha, that's because I've saved the trickiest one for last. And this is the one that the multiplication rule is based on. Okay, are we ready for something even more exciting and challenging? All right, here we go. We're going to introduce the concept of the conditional probability. So now here's what this is all about. This means, let me write it down here. What is the probability of A, given that B is true? This is known as a conditional probability. Now, even that's kind of an abstract example. So let me throw something in there, which is not based on our business school. Let's try this as an example of a conditional probability. Now, suppose you were told, what if it turns out that on a nice day, the probability that you are late for school is 5%. On a rainy day, that probability rises to 20%. Let's say because you've got a long commute and it makes the roads very slick and there's a lot of traffic and blah, blah, blah. So what I'm saying to you here with the conditional probability is, what is the probability of being late? And then this is the key, given that it is rainy. So in other words, the first probability is what we would call unconditional. The second one depends on knowing that it's raining. So that would be the 20%. Because it's raining, we know for a fact that the probability changes to 0.20. And so that is an example of a conditional probability because it depends on whether or not it's raining out. The first one does not. It's just a general probability that on average, you're late 5% of the time for any reason, because you woke up late, because it's bad weather, whatever, because your dog needed to go for a walk at the last minute. You know, there's all kinds of possibilities. And so the conditional probability just simply means that we want to know the probability of one event occurring with the information that another probability has, or another event has occurred. So what I'd like to do now is show you how this would work with our students. Suppose I want to know the probability that a randomly chosen student is majoring in marketing, given that he or she is getting a bachelor's degree. Now, this is very different than what we've been doing. We're told that this person is getting their bachelor's degree. That changes everything because now we can ignore the MBA students. See, then that's the key. So as far as we're concerned, we're not choosing from a group of 500 students any longer. We're choosing from a group of 400 because we know that this person is getting a bachelor's degree. So if you look at this table, remember, we're trying to find out the probability. So let me repeat it up here, that a student is majoring in marketing given that he or she is getting a bachelor's degree. So what you're going to do is find all the bachelor's students who are getting their degrees in marketing. Oh, what happened here? Hold on. No, let's go get the other table. I'll show you this table in a minute. Just to be consistent, let me go get, because what we've done here is there's a second way of expressing this table that I wanted you to see. So let's go back and get the original table for a minute. Yeah, here we go. So let's look at the original table. And what we're seeing here is that the probability of getting a bachelor's degree and studying marketing remember, marketing is T, is 90 out of 500. The probability of getting your bachelor's degree is 400 out of 500. So what we're effectively doing here is taking the ratio of these two. So our conditional probability is the ratio of these two numbers. Oh, what did I do? And so move it down here. That's going to equal 90 out of 500 divided by 400 out of 500, or just simply 90 out of 400, okay, which turns out to be 0.225. Or just doing it visually, you're taking 90 out of 400. You notice how here it's 90 out of 400. So unlike the other examples where we divided everything by 500, here we're dividing by 400 because we've already been told that this person is getting their bachelor's degree. All right. So that's what separates this from the other types of probabilities. The fact that we're given some information which changes the probability, because now the number of students that we could potentially choose from is very different. 400 instead of 500 in this case. So you can see this, yeah, this is the challenging one. Now, there's some notation that I want you to know about. Instead of writing the words, given that, we're going to introduce a new way of expressing this type of probability. The probability, actually, let me type this one. The probability that a student is majoring in marketing, which we know is used based on the letter T, given that he or she is getting a bachelor's degree, is written as, and this is the special notation I want you to see because it really is a very nice shortcut. It's written like this. So this bar is pronounced given that. Okay, given that. So in other words, we're saying here that the information we know is the B. With that information in hand, we want to know the probability that T is true, getting a bachelor's degree in marketing. So this is how it's written. And it turns out there's a formula we can use to figure this out. This is equivalent to saying the probability, the joint probability of T and B, all divided by the probability of B. So every one of these conditional probabilities can be derived from the table using this setup. All right, so while it sounds very complicated, once you've done 2 or 3 of them, you'll begin to realize that it's really not that bad. Okay. So why don't we do this? Let's do another one. Oh, no, let me leave this here for a minute so you can catch up. Then we'll just pick another one to do. All right, so let's think of another one. Suppose that we have this. The probability that a student is getting an MBA, given that he or she is majoring in finance, let's say. Okay, so we would write this as so remember, this means given that. This is the known information. And the formula tells us to do this. Okay, so now all we have to do is go back to the table and look them up. So let's see, let's come back here. Ignore, the circles here. M and F is, actually, I'll tell you what, let me just copy this. It'll be cleaner that way. Okay, so remember, we're looking for the probability. I'll write it up here again. Okay, M and F is here. That's 45 out of 500. And F is this total. So that reduces to 45 out of 175. And that is equal to 0.257. Now, again, the reason why we're spending so much time with this is because the multiplication rule, which is what we're building up to, is defined in terms of conditional probabilities. And that's why we have to truly understand what they mean before we use the rule. Otherwise, none of this will make any sense to anyone. Now, I do want to point out one more thing too. The way this table is structured, if you notice, every time I do a calculation like this, I'm going to end up having to divide by 500, and then those will simply cancel each other out, which is a bit of a nuisance. So sometimes what we see with these tables is that we can divide the 500 out in the beginning before we do any calculations. And if we do that, we end up with this table. Let me just find a home for this. Here we go. So here's what we can do. The table can be simplified by dividing all the numbers by the total of 500. So now here's what happens. Instead of having the actual counts of the students, all of these numbers are all probabilities. So if, let's say you only need the probabilities, let's say you don't really need to know the exact number of MBA students majoring in accounting. You just need to know that 7% of the students are in that category. This table is probably the easier one. If you do need to know the actual numbers, well, then of course this isn't going to help you. So, but if all we're interested in the probabilities, then this might be a cleaner way of calculating our probabilities. So just a quick review, remember before we did marketing, given a bachelor's degree? So this time we don't really need to divide by the 500s. With this table, we can just take the 0.18 and divide by 0.80 to come up with our result, which is 0.225. Okay, so the reason why I'm bringing this up is because I think the examples that we'll be seeing on the practice problems in the exams are going to be based on this type of setup, where the table has already had the totals divided out so that what's left is probabilities, but it's the same thing. I think this way is just a little bit maybe simpler. So we may as well stick with this approach. But still, like I said, if you really did need to know the actual numbers, then you can't do this. All right, okay, now, with all of that in place, we finally can use the multiplication rule. So let me just show it to you. It's written in two different ways, two equivalent ways. Here's the first version. And you'll see right away, there's a reason why we went through all this trouble, all this background information, because guess what? We need, it's defined in terms of a conditional probability. And if you recall, this is a joint probability. And this is what we called an unconditional probability. Okay, so that's why we needed all that information about joint probabilities and conditional, I mean. Now, the equivalent version of this is on the next slide, and you see what this is basically showing us is the order is not really important, because there's two equivalent ways of getting to this. All right, let me show you the second version. And in fact, while we're at it, let me just put the first version back in here so you can see them side by side. they're both going to give us the same information, but in some cases, one is more convenient than the other. So you can pick the one that makes the most sense. One thing I did want to remind you of, though, is that when it comes to these joint probabilities, the order in which I write this doesn't make any difference. Okay, same thing is true with unions. Okay, just in case there's any confusion, these all mean the same thing, all right? A and B is B and A union B is B union A. All right, finally. So we're ready for an example. So let's see. Okay, so let's look at a case where we're choosing a card from a deck. And let's say that we define the following events. A is the card that we choose as an ace, and B is the event that the card is black. Now, if we want to calculate a joint probability, A union B, A and B is the event that the card is a black ace. In other words, being both black and an ace means being a black ace. So how do you calculate this probability? Well, we need the multiplication rule. And we can use both definitions of the multiplication rule to do this. All right, so let's do that. So let's say we decide to use this approach. Then we need to know two things. What's the probability of A? Now remember, this is an ace. 4 out of 52 cards are aces, which gives us a probability of 1/13, which means we still need this probability. And so B given A means the probability that the card is black, given that it is an ace. Now for this, we'll have to use our intuition. If you have the aces in front of you, 2 of them are black and 2 of them are red. So therefore, B given A must be a half. Okay, 4 aces, ace of spades, ace of clubs, ace of hearts, ace of diamonds. These are red and these are black. All right, so we determined that B given A is 1/2. And now we can combine these results using our very cool multiplication rule. And guess what? We've got the 1/2 from B given A and the 1/13 from A. And it turns out that the chances of that happening are 1 out of 26 or 0.0385. Which shouldn't surprise us because there are 2 black aces in the deck. So 2 out of 52 is 1 out of 26. So of course that has to be right. All right. All right. Now, what if I do the opposite approach? The second version. Will I get the same results? Of course. But now I need different information. B has a probability of 1/2 because remember, B is the probability that the card is black. That's 26 out of 52 or a half. Here's the interesting one. if I have all the black cards in front of me, 26 of them, 2 of them are aces. Two of the 26 black cards are aces. Therefore, the probability of A given B rather is 2 out of 26. Or 1/13. So you can see what I can do now. Ah, it's 1 out of 26. What do you know? No surprise. All right, now we're not completely done. I see we're just about out of time here. There's one last concept that we need to consider, the notion of independence. So I don't want to rush to that. So here's what I'd like to do. Given that we don't have a class before Thanksgiving, that means the next time we meet will be the last time before Thanksgiving. So we don't have time to waste. So what I'd like to do is go back to my announcement and maybe, let me see, I don't remember already what we said. I was afraid of this. You know what we still have to do? Actually, maybe you can wait. I'll tell you what. Why don't we do this? Oh, God. Let me just write this down on a piece of paper or something. This is so confusing. Trying to squeeze everything in. So today's the 10th. Actually, that's 12/1. All right, here's what we'll, oh boy, we've got one more chapter coming up. So let's say if we agree that on the 17th, we'll do the sample midterm number 2. And then with whatever time is left over, the new chapter will start. Here's Thanksgiving. Oh, and yes, you know what else we're going to do? We're going to go back and finish chapter 11. In other words, we're not completely done with 11. We still have one more thing to do. Then we'll start the new chapter and we'll do the sample midterm. All right, fine. On the 1st, then we'll do the sample chapter 11 problem set. We'll finish the new chapter. I think it's 12, but I have to double check. And then on the 8th, we can do the chapter, the new last chapter, or the new chapter problem set. And again, I think it's 12. And the sample final. All right, I think we can just about squeeze this in. All right, I don't remember how long chapter 12 is, but it's not maybe as long as this one. So sadly, we're almost done with the semester. So that's why we have to be so careful here. All right, so let's use this as our guide.
Excuse me.
Yes.
Is it okay? I'm just asking. Is it okay? Can we like, I don't know, can we like submit the midterm like in like on Thanksgiving weekend? Is that cool?
Sure, absolutely. You can send it in,
Oh,
please.
okay, because it's like me personally, I don't care whether I do the midterm during break or not. You know what I mean? I just want to make sure I have the time to complete it. That's
Yes,
all.
I get it. Oh, no.
Thank you.
If you're able to do it during Thanksgiving break, please do it. It's just that I don't want to make it, like I don't want to force people to do the stuff. Maybe you have travel plans or something. And
No, I understand.
So what I'll do is I'll just say, listen, you hand it in as soon as you like. but it won't be necessary to have it ready until we get back. Like it was the 5th, I believe. No, the 3rd. Okay, so yes, you always have the option of sending it in earlier. So if you think that you're going to have some time to study during the Thanksgiving break, then you may as well don't let it go to waste. I'm happy to see it come in earlier. That is definitely not a problem.
I have one other question. I see that you said for November 17th, the sample midterm is going to be like up there, right?
I actually just sneaked it in there while you.
It's already uploaded.
It's already here. I just sneaked
Oh
it.
no, I was going to ask if you could upload it now, but never mind. That's fine.
It's
I
there.
want to get early look at it. That's why.
It's right here, and when you look at it, you'll see, like I said, it's almost 100% chapter 4. Just a few questions about 5.
Thank you.
Okay, it's there, so you can start working on it right away. All right, anybody else? All right, so that will be our schedule, and I think we can just about finish on time. It's gonna be right down to the wire, but we'll do it. We'll be done with everything, and then you'll be ready to roll into whatever math class comes next. Possibly Calc 1 would be next, actually, or you can take an entire semester of statistics if you like. But hopefully something else is in your future. And even if not, all these wonderful concepts will come in handy no matter what you end up studying. So, all right, anyway, I guess I better knock it off here, and I'll see you all next Wednesday. Okay?
Can you make sure you have my midterm to show you my work part?
Oh, yeah, let me,
Yeah.
where did you send it?
I sent it to both Alan Anderson and the Dr. AA. It's a John Pillsbury one.
What time did you send it?
Yeah, I just sent it on what?
Is this,
11:14. Wait, no. I sent it 11:24. Yeah.
all right.
Like earlier, I sent it to the same email link with the midterm that you just saw. Like when we were on break.
You know what? I bet they jumbled them all together. I bet, is this?
Yeah, I try to keep it all together.
All right, it's here.
Yeah. Okay. I just want to make sure you got everything.
It looks like I do. Okay, good.
If you need something else, please let me know. I'm always looking at my emails.
Okay, good.
Thank you. I'm sorry.
All right, that's okay. All right.
Yo, you have a
anyone
good
else?
weekend, man.
Okay, you too.
Thank
Anyone
you.
else have any questions? Okay, then I'll see you all next time.
Thank you, Professor. Have a good weekend.
Hey, bye.
I'll see you on Friday, actually.
Oh, that's right. Okay, see you then.
See you then. Bye.